So we're going to look at solving some first-order differential equations. So we first think, well, what does it mean to be a first-order differential equation? Well, it means the derivative is a first derivative. There's no second derivative, there's no third derivative, only the first derivative is involved. Or sometimes the problem may be written in terms of differentials, as we will see. So if g of x is a continuous function, then if the differential equation is y prime is equal to g of x, it can be solved by simple integration. So the solution would be, if y prime is equal to g of x, then y is equal to the integral of g of x dx. And then, of course, we don't forget the constant, the plus c. For instance, if y prime is equal to x sine of x, what are we going to do? We're simply going to integrate x sine of x. Of course, that means we have to remember our integrations. And to integrate x sine of x, how do we do that? Well, that's going to be what method? Hopefully you can recognize that that's going to be an integration by. So we're going to do y is equal to the integral of x sine of x dx. To set up our integration by parts, we do u is equal to x, dv is sine of x dx, then du is dx. V, how do we get v? We integrate sine of x, so that's going to be minus cosine of x. And then the integral of x sine of x dx is going to be u times v, so minus x cosine of x, then minus the integral of v du, so minus the integral of minus cosine of x dx. So we integrate that, and we end up with y is equal to minus x cosine of x plus sine of x, and then of course we have the plus c. A differential equation of the form y prime is equal to g of x divided by h of y, or it might be written in terms of differentials, so it may be h of y dy is equal to g of x dx, or it may be some variation that if you move things around you can get it in one of those two forms, is said to be separable. So the idea is going to be, we're going to put all the things with the y on one side of the equal sign, all the things with the x on the other side of the equal sign. We're going to separate the variables. Now, we would end up with y prime is equal to g of x divided by h of y. We would end up with h of y times the derivative of y is equal to g of x. Then we're going to integrate both sides with respect to x, not forgetting the plus c. Notice on the left side we end up with the configuration y prime dx. Y prime dx, if you go back to calculus, is the definition of the differential dy. So the y prime dx we can replace with the dy. So we'll have the integral of h of y dy is equal to the integral of g of x dx plus c. Let's look at an example. So let's say we have dy dx is equal to y times e to the 2x. So we're going to have to think, can we get all the y's on one side of the equation, all the x's to the other side of the equation? And then, of course, we have the derivative there. Remember, the derivative is defined to be one thing, not the ratio of two things. So we move the y over, and we get 1 over y times dy dx is equal to e to the 2x. We're going to integrate both sides with respect to x. And notice the derivative of y with respect to x dx gets, by definition, is the dy. Now, what does it look like you just did? It looks like you multiplied both sides by dx. Left the dy on the left and got the dx on the right. Technically, that's not what you're doing. However, the notation is so nice that you can do it that way and get the right answer. Now, some other people in other areas, not naming any names, but maybe in physics, let's say, they will multiply both sides by dx and not even think about it. In math, we will at least recognize we're kind of taking advantage of the notation. We'll still do it. It's just we'll recognize we're actually abusing the notation. So the left side becomes the integral of 1 over y dy is equal to the integral of e to the 2x dx. We integrate 1 over y dy, get natural log of the absolute value of y. We integrate e to the 2x, get 1/2 e to the 2x. And then, of course, do not forget the plus c.